I'm Mark Smith, and this is my presentation as part of my master's project on the presence-only modelling of the lapwing in support of local biodiversity action planning in the UK. The issue I'm tackling relates to biodiversity, and in particular local biodiversity action plans that are one of the main tools used in the UK to reverse the decline. These action plans, although strategised at a national level, are enacted in partnership between local authorities, such as in this case Warwickshire County Council Ecology Unit and Warwickshire Biological Record Centre, in partnership with NGOs, in this case Warwickshire Wildlife Trust. This means that the teams that carry out these action plans, that are for species and habitats, cover a range of aptitudes and skills, and have a range of talents that are inputted into the team. Quite often a team is just a single person working not necessarily full time, but with a range of skills available. The data also is often quite low quality. Although there are national schemes like the Breeding Bird Survey, national mammal monitoring schemes, wider countryside butterfly survey, there's an issue that the key data for many taxa is present only in nature, such as the lot that's from the NVN, and so therefore of lower quality, but still useful in terms of conservation planning. So the objectives for the research was to create a habitat suitability model for two techniques, and these techniques were a habitat suitability index and a machine learning algorithm called Maxent, to see if they're a useful tool to be used in local biodiversity action planning. These models need to be validated, and the output will be a suitability map for the lapwing for Warwickshire. And the third objective is an evaluation of the two techniques in biodiversity action planning. So let's have a look at the framework I used. I chose the lapwing as it's a key species that's been in decline, down by 40% since the mid-1970s. There's been some resurgence in fortunes in Warwickshire, but it's still a threatened species. I used Lowland Britain as a biogeographical extent for this model. The map in the corner here shows the extent of data I used. For presence data, I actually went for a solid data basis, and I got that from the Breeding Bird Survey run by the British Trust for Ornithology, which surveys 1 kilometre squares across the country. Because I'm using the Breeding Bird Survey, which is run from 1994 onwards, the data that I derived for the presence ran from 1994 to 2017, so that became my temporal resolution. So all data sets that were inputted into the model had to be within that time frame. And lastly, the key point to understand is that for Warwickshire, which is this sort of region here, the presence data was removed from the planning and building of the model, so that those presences could then be used to test the validity of each model. The first model I applied was this Habitat Suitability Index, which is a long-held study technique developed by the US Fish and Wildlife Service in the 1980s. They've developed hundreds of these for many different species. In this country, we've only used it for the great crested newt. It uses a range of predictors to correlate the idea of this correlation between where the organism of interest is found and the underlying environmental data and properties in which it is found. And then you're using techniques such as general linear models, regression techniques to create a predictable model to extrapolate across a wider area. The predictors then. This is the list of predictors I used, or at least started to look at. You start with a large pool of predictors and try to whittle them down depending on the particular orthicology of your species. And the way to decide which predictors to use, I use a correlation with a random sample. So I mapped the presence of the lapwing, calculated the values for each lapwing 1 kilometre square, what's its elevation, what's its slope, what's its aspect, etc. I then ran several random samples, you could say pseudo presences for lapwing, and correlated the two, did a statistical test against the two. And what you end up with, I used Mann-Whitney U and chi-squared as the statistical test. A significance value tells you how good that particular variable predicts the presence of a lapwing. And you get some very strong correlations, particularly for elevation and slope. The soil data is particularly good, but you also get identification of areas where there's no significant impact upon them. So slope density, crow incidence, magpie incidence, all predators of the lapwing have no effect. So these were dropped from the analysis. From each of those, you get a response curve for each of these predictions that you can then use to build your model. So in this case, on the left, you've got continuous data, that's graph, and you can use linear models or log transformations or curvilinear models. I use actually some mathematical modeling software to create equation formulas for continuous data that correlates to a HS value, which is habitat suitability, 0 being unsuitable, up to 1, which is very suitable. For categorical data, I use bar charts basically with a weighted function to give the same thing with your HS value if you're high or low. You can then plug these into a simple additive method. There are more complicated methods which have their positives and negatives, but in this particular case I used an unweighted simple additive model. So, for instance, elevation is part of the terrain suitability, which is H1, so that's the total value of that will go into there. And habitat is H7, that will go into there. And then you basically add up each of your points, divide by the number of these that you've got, 7 in this case, to give you a final score of suitability from 0 to 1. Maxent, on the other hand, this is a machine learning algorithm program developed by Phillips back in 2006. It uses and inputs just the raw raster maps. So each of those environmental predictors were rasterized, the same presence data was inputted, and then you can make multiple runs, varying the number of times it runs the model, the iterations, the amount it uses test data. There's hundreds of different parameters that you can tweak. And that then spits out, not a general formula, but it gives you its own map of where it believes suitability. In this case, blue is unsuitable, the lighter colours indicate greater suitability. It shows you which points were used to train the data, in this case the purple and then the test data, which is the white square. Probably most importantly is this graph that it produced that helps identify how good your model is. This is your AUC curve, your area under the curve. What you're looking for ideally is a curve that is as close to that as possible. In this case, we've got our test data, which is the figure we're looking for, which is 0.658, and ordinarily you'd be looking for a lower threshold of 0.7. So we're actually under that with this. Not by much, but enough to suggest that there's probably a little bit more going on with the data. It strikes me that there's perhaps something missing from the predictors, that a key predictor is missing, or something's not quite being inputted correctly here. But it does at least show that it is better, that what the output is produced is better than chance, which is this line here. Okay. So you come on to the results, and the results here illustrate the HSI model here on the left and the Maxent model on the right. They both look incredibly different. Intuitively, the HSI model looks right because you've got unsuitability in the conurbations, in the valleys here, the Avon Vale and the Thames Valley here, you've got better suitability. However, when we input the presences of the Lapwing data for the county. You then correlate that against a random sample and statistically test it. You get no significant difference in this model. So the model is no different than having a random sample. So it's not very good. Although it looks correct, it's not very good for predicting Lapwing suitability. Maxent, on the other hand, as we know, the area of the curve says it's quite good at predicting. And when you do the same thing you predict against a random sample, this actually does come out as statistically different. So this map here is saying something, even though the main conurbation area drops out, although it does pick up solid hold. Veils aren't, the Asian veils are not as strong. Tame value continues to be good, but it does also pick up this pasture land here, which does kind of fit the understanding of the life history from Lapwing. So what are the conclusions then? Simply put, I would say HSIs are complex and they require a broad range of mathematical skills and mapping skills, something that not necessarily all action planners will have, and it makes it a very time-consuming model to prepare for multiple species. In this case, I just used one species, and that took a lot of time. So the Maxent model was the best, and it did give weekly positive data. There's definitely a correlation there. The output is brilliant. It gives you a lot of information with regards to how you can train models to improve, what factors are important, what factors aren't important. Something that as a action plan worker you could very easily use and run multiple times for multiple species. That concludes it. Thank you very much for listening. Thank you. Bye.